and he will talk about multiphysics, his multiphysics project. Bean will also share an update on HPC things with FerriteCon. Okay. Oh, sorry.
Yes. Thanks for the introduction. My research is about cardiac multiphysics, and I will show you a nice introduction into my framework and cardiology, and how we do it on top of Ferrite, hopefully efficiently. So let us start with some motivation. Cardiovascular diseases are the killer #1 worldwide. And since people usually don't directly die of heart diseases, it also causes some economic damage or full socioeconomic burden for us, because these people slowly degrade, basically, which isn't so great. What we do is we take computational models, and with these computational models, we try to investigate cardiac function to understand the heart in the healthy and disease state more properly. For example, what we can do is we can make CT or MRI scans of animals or even the human. Then we have the geometries of our heart, torso, and we can recompute the ECG signals to understand better how the ECG and ECG waveforms relate to cardiac function in health and disease, for example. Especially the challenges in cardiac multiphysics are that we have multiple temporal and spatial scales, because the heart, as most of you know, it's an electromechanical pump. And we have electronics, which is a very fast component, and we have a mechanics, which is comparatively a slow component. And also we have multiple spatial scales. We have the heart pumping, and also what we have is this tiny ion channels on the heart cells, which open and close on a much faster time scale. This also introduces some multiphysics, since we have coupled electronics and mechanical problems, and we also have many uncertainties, because biological systems are inherently stochastic. So the goal of this project is that we develop a flexible computational environment to explore this cardiac function on top of Ferrite. So first, how does the heart basically work? We have a 4-chamber system with some vessels going in and out, we have blood streams, and what basically happens is that, as we see on the right, I guess the video doesn't play on Zoom. Okay. What we basically have is blood flows into the atria, which are small heart chambers. The atria contract first, pump the blood into the ventricles, then the ventricles contract afterwards, and they push the blood through the through the vascular system, for example, through the lungs to get oxygen, and through the body to deliver the oxygen-rich blood to our organs. How does this work? We basically have some conduction system in the heart, which orchestrates the contraction. Because what basically happens is you have an electric impulse, and after the electric impulse, heart cells contract, which makes the whole heart pumping the blood. And we start with the sinoatrial node, where the electrical signal starts, usually in the healthy case. Then it goes over the atria, the AV node, and through the His bundle, Kennedy bundles, Kennedy fibers. And on this simple diagram, we already see from a computational perspective what we have achieved, that we can, each of these generated signals, we can relate back to the generated ECG signals, which we can measure on the body. So how do we basically handle this one? We have the mechanics and the electronics. And one common scheme which we often see is multi-mesh type operator splitting, where we say we have a slow and coarse component, which is the mechanics, and we have the fine and fast component, which is EP. So we separate these. And the solution scheme is basically what we solve a mechanics problem, however it looks like, how we model it. Then we transfer back the fiber stretches, because the EP is sensitive to fiber stretches. When we solve on the fine mesh, the EP problem, possibly multiple time steps, and transfer back the calcium, which is the component which is responsible for the contraction. How can these physics, for example, look like? We usually have most partial differential equations. On the top, we have part of a monomain problem where we see we have some diffusion operators, we have some nonlinear source parts. We have some internal variables appearing here with these two, and they have sometimes a nice special structure which we want to abuse when we develop solvers, and we have some nonlinear mechanical part. And as I've shown on the previous slide, we decouple the mechanics additively from the electrophysiological part. And again, usually the EP part is again solved with some operator splitting, where we decouple the linear diffusion problem from the nonlinear internal variables, which gives us very efficient schemes. So how do we put this one into software? Basically, the rough workflow in Thunderbolt is that we start by defining some model with boundary conditions. Boundary conditions might also include our coupling conditions. How do we couple, for example, the FSI? Or how do we couple the electrophysiology with the mechanics in detail? Because I just said it's something with calcium, but I haven't given you details. We want to leave this open because there are many ways how we can model it. Then we load or generate some mesh, which is annotated, as we already know in Ferrite, where we have, for example, the subdomains marked. This is heart, this is the torso, this is the lung, and so on. And this mesh has to provide the correct annotations for our model and boundary conditions, which we define on the different subdomains. Now, in cardiology specific, we have very special coordinate systems. Usually we don't work on Cartesian coordinates, but in so-called generalized coordinate systems, where we, for example, have an angle from -1 to 1, which says left to right, or bottom to top in the heart. And together with the coordinate system, we also put in a spatial discretization technique to obtain a semi-discrete problem, or a discrete problem, depending on whether we had time derivatives in it or not. And finally, the discrete problem is taken to the solver. Optionally, if it's time dependent, we also need the initial condition to close the system. And it is rather simply here, as we see, for example, I don't know if it's possible, we define a monodomain model where we have constant coefficients. We can also define field coefficients. For example, if we have measured fiber data from MRI, we can also plug it in some simulation protocols, some cell model. We generate a mesh. We semi-discretize it with a reaction diffusion split, as I've shown in the previous slide. We use a final end discretization with Ferrite. What's a bit different here is that I provide so-called collections, which just says I want to use Lagrange, whatever element I have underlying, be it TET or hex, for example. And then I just define a solver, which is some combination of the operator splitting solver, since we have a reaction diffusion split, and for each part of the split, I define the solvers. And then I put everything together into the solver, which is very familiar for some people. And this one is basically the interface for SciML. And also, for example, the Trix people also developed this specific interface. They just have the initializer also in the discretization. That's the only difference here. So what have we achieved? We, for example, have investigated different active contraction models against experimental data. where we took rings, which can be seen as if we slice through the heart, we just get a ring, because the chamber is basically just some rings stacked. And we get pretty close to the experimental data through the cardiac cycle. As we see here on the right, I don't want to go into details since I'm a bit short on time, I think. And the same for idealized left ventricular models. We see similar phenomenon. We can vary the setups with different boundary conditions, different cell models, different calcium couplings. And for many of the models which found literature were already implemented, we see that similar issues occur, which we are currently not able to solve because there are some things about cardiac function which we don't understand very good yet. So about a bit about the implementation details, we have the user-facing side, where some things are a bit different than in Ferrite as we have already seen. Instead of a grid, we have a mesh, which is basically a grid plus some topology information. Then instead of interpolations, we have interpolation collections. For example, we say we have a Lagrange collection instead of Lagrange ref triangle and so on. Same with the thresholds and the cell values. So we have for the user-facing side a nice abstraction layer. We have PD-dependent extension points. For example, if we have elasticity type equations, we usually just want to define energy, and everything else can be automated here. We also have mesh generators for the common geometries, for example, for the idealized LV and the ring. They are hand-optimized generators, which generate very nicely structured grids. We have coordinate system generators for all the specific cases, and we have the CellML toolkit integration to import all the existing CellML, not all, but many existing CellML models just into our framework and use it directly. Internally, we have an abstraction layer around operators, which basically abstracts away how we parallelize or how do we use application of an operator to a vector, which can become handy once the matrix-free stuff takes off. We have, similar to what Knut does, element routines, which are somewhat physics dependent, where we control the dispatch also through caches. And we have many helpers to deal with all these operator splitting strategies. For example, transferring the solution between meshes and having this specific splits, which we know in literature. But the internal still needs some work. And one of the related issues is the nonlinear solver interface issue from ordinary DiffX, which we are currently actively trying to solve. So as a summary, I've presented you a flexible software framework with a clear separation of concerns. I hope that we get an efficient shared memory parallelization with these operators. For threaded assembly, we know it's still subpar, but I think this is a solvable problem. And we have an easy extendable modeling layer for the modeling users. So what we really want to achieve here is to simplify the interaction between modelers and the guys who develop the numerical schemes. Because currently the communities are a bit separated, which is not so optimal. As the next steps, I really want to push the AMR and GPU integration. I want to fix this interface against SciML, which is a long open issue. We also want to add more state-of-the-art solvers to have really, hopefully, fair comparisons between different techniques. So we are all in one framework and we can really specifically test. And also some components are missing. For example, I don't have pulse dynamics and dot dynamics implemented yet, which is also a rather big problem. So in the end, I hope that we can, in the near future, deliver fast cardiac multiphysics simulations. And with this, I want to thank you for your attention.
Okay, any questions? How much of Ferrite are you actually using? How much of you have to be implemented?
I mean, the framework is quite big. It's about 15,000 lines, but it uses quite a bit of Ferrite. So, I mean, for the assembly, for all the stuff distribution stuff and so on, I mean, some of the stuff I plan to contribute upstream to Ferrite once it takes shape. For example, we had this longer discussion about whether we should materialize faces and edges or not, which can then speed up, for example, DOF distribution, which now we can benchmark stuff, really look if we want to contribute it back. And for example, I also have, if I materialize the stuff, I can do something like uniform refinement very easily, which is with the current grid a bit tricky. But yeah, I'm using almost everything which Ferrite currently delivers. Also subdomain management. Yeah.
Okay, and more questions?
Perfect. No? Okay, then let's thank you for this part of your talk.